In this video we're going to discuss something called Newton's method. And it's a little bit of a change of pace from some of the stuff that we've been looking at up to this point. In the last few sections we've been using a lot of algebra to try to help us with calculus. You know, we take derivatives and there's a ton of simplification. We take derivatives, set them equal to 0 to find our mins and maxes, and then do a bunch of algebra. So algebra is sort of an ever-present part of calculus. The question is, can we use calculus to help us with algebra? And in a sense, the answer is going to be yes, and that's what Newton's method is going to be all about. So, can we use calculus to help us with algebra? And the answer is, again, yes. Okay, so for example, maybe we're interested in solving something that looks like this. I want to solve x cubed minus 3x minus 4 equals 0. So we've got a cubic equation. And it's not immediately obvious to me looking at it that it's going to be something that we can factor. It's not like we can pull an x out of this whole thing. And in general, cubics are a pain to deal with. It's possible to solve these cubics. There's a formula developed by an Italian Renaissance mathematician named Cardano back 500 plus years ago. But most people don't know it, and it's actually really, really bad anyways. And if this happened to be a higher order polynomial, like a 5th degree polynomial we were dealing with, there is no closed form solution at all. So long story short, problems like this are difficult to deal with, and if we make it pretty much any more complicated than it is, it'll be impossible to deal with using traditional algebraic techniques. So we're going to be able to use calculus to help in kind of an interesting way. So we can use calculus to help solve this using a computational method, so meaning we would be using a computer. So by using a computational method, there we go. Computational method called Newton's method. So let me give you a sense of how this works. The easiest way to see how it works is visually. So how will this work? So let me give myself a little room here and draw a graph. Imagine this is a function that we're dealing with. So here are the x and y axes for this thing. And we've got a graph that looks something like, I don't know, does something like this. Here's our function over this region, some y equals f of x. The way that we're going to solve this is to think about what it means graphically to solve it. So if we look at the equation that we have up here, we've got some sort of f of x, in this case a cubic, set equal to 0. And graphically what that means is we're looking for the zeros, the points where the graph itself goes through the x-axis. So basically we want this point. So we want the x-intercept. This is where So our f of x is equal to 0. This is what we're trying to solve. So how do we do that? What we'll do is we'll start by just taking a guess. And maybe the guess for where that 0 occurs, I guess right here. And I'm going to call this point x1. And obviously it's not a very good guess because the function value at x1 isn't 0. Instead, it's all the way up here, whatever this value is. But what I'll do is compute the derivative of my f of x and use that to come up with a linear approximation, and I will draw the tangent line. So we've done this in the class before. I'm going to draw the tangent line. Here's the tangent line. So this line is our linear approximation of f of x at x equals this first point, x1. And what I'll do is I'll follow that line down and see where it hits the x-axis. And I will use that point for my second guess, x2. And I will repeat the process. I'll say, okay, well, let's go see what the actual function value is. It's not 0, but I'm going to go to that point. Let me look at its tangent line, which goes this direction. And so here's a second linear approximation. It'll give me another point, x3, and you can see we're slowly zeroing in on the correct value. We would repeat this process over and over and over, and eventually we would arrive at the actual point that we're interested in. So this is how the process of Newton's method is going to work. We want to set f of x equal to 0. That's what we're trying to find. So how do we do this? Not just sort of heuristically and graphically, how do we do this actually using calculus? So let me give us a little bit more room. Okay, so again, we want f of x equals 0. And so the x-intercepts of f of x. Oh, come on, pen. There we go. So that's what we're trying to find. And we'll start with that tangent line. So our linear approximation at x equals x1. So we're going to guess x equals x1 is our 0. So our x-intercept. And as we saw, it's probably a wrong guess. And so what we'll do is find the linear approximation. And our linear approximation is going to look something like this. So the point slope form of a linear approximation would be something like this. So here's our point slope form of that line. All we need is a known point on the graph. So these points here are some known point, which we'll have. And there's our slope, which we can find by taking the derivative. So those are the pieces that we need. For us, m is going to be equal to f prime evaluated at that guess, x1. So our slope is just the slope of the function evaluated at x1, where our initial guess is. Our known point, x naught, y naught, turns out to be x1. That's the x value of the point. So going back up to the graph, I want the coordinates of this point. The x coordinate is x1, and the y coordinate is just going to be whatever f of x1 is. So we've got x1 comma f of x1. So there's our known point, which gives us the tangent line. So putting these together, we get our tangent line that looks like y minus f of x1 is equal to f prime of x1 times x minus x1. So this is the equation of the tangent line that we drew earlier. And we want to figure out what its intercept is, because we want to trace this line. Here's the line that we just found. I want to trace it down to where it intercepts the x-axis. So here's the line that we're dealing with right here, and I want to know where does it intersect with the x-axis. So basically, what is the x value when the y value is 0? And so we can essentially just plug in that point. So what is x when y equals 0? That's what we're trying to do. And so if I take a look at that equation, just plugging that point in, we're going to get 0 minus f of x1. There's all I've done is plug in y equals 0. And that's equal to f prime of x1 times x minus x1. And we want to solve for the x. So I want to solve for that guy right there. Okay, so how do we solve for this? The first thing we need to do is right now our x minus x1 is being multiplied by the slope here, the f prime of x1. So I want to divide, undo that multiplication by doing division. Divide both sides, and we will get on this side negative f of x1 divided by that f prime of x1 is equal to x minus x1. And then our next step, to again isolate the x by itself, we're subtracting x1 from it right now. I need to undo that subtraction with an addition. We'll add x1 to both sides. And I'll wind up with x is equal to x1, after I've added that to both sides, minus f of x1 divided by f prime of x1. And this gives us the relationship that we're looking for. Once we've found this point x, if we go up to our picture again, we've now just found this point, and what did we call that point? We called it x2, and then repeated the process. So this is what we call a recursive process. We're going to repeat it over and over and over, getting successfully starting with x1, using x1 to get x2, using x2 to get x3, using x3 to get x4, and slowly zeroing in on the actual value that we're looking for. So this is going to be, I guess maybe a better way to call it is not recursive. This is an inductive approach. So we're going to let this x be equal to x2, then repeat the whole process to find x3, etc. We'll go on and on and on. So if we repeat this over, repeating this indefinitely, we'll eventually zero in on the correct answer. So let's write it this way. If we repeat this over and over, we'll get a formula for the n+1th approximation. So instead of talking about the first guess, which was x1, and then our second guess x2, and our third guess x3, these are all successively better guesses for the root that we're trying to find. We'll find the n+1th approximation as follows. It'll be our xn plus 1. So I'm going to use subscripts the exact same way that I did here with the 1, 2, 3, and so on, but now I'm generalizing it to n's and n plus 1, n's and n plus 1s. So I'm saying that xn plus 1 is going to be equal to xn minus f of xn divided by f prime of xn. And this gives us our inductive formula. You give me any guess xn for that root, and I can give you the next guess, n plus 1. Okay, so one thing that we've kind of neglected up until this point is in our example, it made it really obvious that this approach was going to work. We were going to go from a bad guess to a better guess to a good guess to a great guess, so on and so forth. And we could eventually get basically arbitrarily close to the true value, as many decimals of accuracy as we want. But is this always going to be the case? Does this always work? So does this always work? The answer is no. So the term that you'll hear talked about in this case is the idea of convergence. Does xn get closer and closer to the true value that we want as we repeat this process over and over and over again? So if xn goes to this true correct value of x, which I'm writing as sort of the real root that we're looking for, the real 0, if xn goes to that number as we repeat the process over and over again, so as n goes to infinity, then we say in this case the sequence of answers that we're getting converges. Our sequence of approximations converges to the correct answer. So that's one possibility. But if xn does not approach x as n goes to infinity, our method fails. And this can happen. So let's look at a couple of examples of where it's not going to work, and then I'll see if I can also give you some examples of where it will work. So here are some examples of Newton's method failing. Okay, the first one I want to look at is the following. So here's our examples. Here's our first example. I want to think of f of x as the following. It's going to be x to the 1/3 power. So basically, we're looking at a function that's the cube root of x. If we graph that function, the cube root of x, this is what it winds up looking like. So I'm giving myself a lot more room on the x-axis than the y-axis due to the shape of this thing. But the graph looks kind of like a square root, but it has this odd symmetry, and it is defined for negative values of x, unlike a square root function. And so we can see what will happen here potentially if this is the point that I'm trying to find. Right, we can see by observation it's going to be the origin. The origin is where the 0 of this function is. So here's my f of x. Y equals f of x. And I'm trying to find, again, the 0 of this function. So let's say that our first guess wound up being here. Here's our x1. And what I do is go up to the graph right there, pick that point, draw our tangent line. Our tangent line looks like this. And we hit this point right here. And so this is going to be my x2. And from x2 we would do the same thing, go down to the function, find the tangent. The tangent here, let me go through it, is going to wind up hitting over here. This will be my x3. And I'll go back up to the function there, find this point, do the tangent line, and the tangent line winds up being way over here. Here's my x4. And we would continue on in this pattern repeatedly, but you can see that x1 of all of these guesses was the closest to the correct answer. It was wrong, but it was closer to 0 than any of the others. x1 was bad, x2 was worse, x3 was worse than that, x4 is even worse than that, so this is not converging. So visually, if this number was 1, if 1 was our first guess, you would see this exact same type of pattern happening, and you would see that x2 would be a number that would be negative, but it would have a larger magnitude than 1. It'd be, I don't know, negative 1.5 or something like that. I have no idea. I haven't actually done the actual numbers on this. But you can see we're getting further and further away. We started here, get a little further, get even further, get even further, and this would only get worse as we continued. So why does this happen in this particular case? So why isn't it working? In this case, one of the big issues is that it turns out our f of x, so in this case, f of x isn't differentiable. At the point that we're interested in, at x equals 0. We can try, so what I mean is, if we try to take the derivative of x to the 1/3, we can find a derivative, that's fine. This is just power rule. We'll get 1/3, the power will come down, x raised to a power that's 1 less than the 1/3 that we had, so 1 less than this is going to be negative 2/3. And so we can write this as 1 over 3x to the 2/3. But when we plug in x equals 0, this basically gives us something that looks like 1 over 0. So we've got some sort of infinity. It's basically the slope is infinity. So plus or minus infinity, depending on whether that's a tiny positive 0 or a tiny negative 0. That's essentially what we're looking at. So essentially, right, this is off limits. The derivative does not exist if x equals 0. This function is undefined at x equals 0. So that's the situation. That's why this particular one failed. What is another possible case? So there's another reason things could go haywire here. Let me just get everything aligned. So second example. Let's say my f of x was equal to some sort of parabola. Let's do x minus 2 squared minus 1. And so if we think about the shape of this one, again, let's do it just graphically here. We're going to have a picture that looks like the following. So give myself a little more room over here on the positive x-axis. Here's our y. We've got a parabola, and we are doing some transformations to it. The -2 here means that we're shifting the parabola 2 to the right, and that's a minus sign. And this one out here means we're shifting it down by 1. So normally if we just had f of x equals x squared, its vertex would be right here at the origin. The vertex of this one is going to be shifted 2 to the right and 1 down. So 2, -1. Here's the vertex of this one. And it winds up looking like this. So here is our y equals f of x. Now see what happens if I let my first guess, x1, be equal to 2. Right, so there are 2 possible zeros. These are the points that I'm trying to find. By observation, again, we could do these algebraically. This one's going to be at 1. This one's going to be at 3. There's where my 2 zeros are. But if I had my first guess be right here at 2, then I would go down and try to get my tangent line, and my tangent line would look like this. Here is my tangent line. Oops. And we're trying to find where that line intersects with the x-axis to get our second guess, but in this case it's parallel to the x-axis, so our tangent line doesn't ever intersect with the x-axis. Right? It doesn't have any zeros, so we're never going to get a second guess. So basically, in our formula, so again, what is the issue? Well, it's because our f prime at our x1, our initial guess, is equal to f prime evaluated at 2. And by observation, I'm not going to go through the actual derivative of the formula and plug in 2, but it's clear that this is going to be 0. And if we go back to our formula for Newton's method, right here, we're going to have to divide by that derivative. And if the derivative is 0, we can't do that division. So in this case, whenever we hit a point where the slope is 0 of our tangent line, we're not going to get something that converges. But this one can be fixed. All we need to do is not pick x equals 2 or x1 equals 2 as our starting guess. So this can be fixed by selecting x1 not equal to 2. Any other value would work. Generally, if we pick a point to start that's somewhere over here, anywhere on this side, we will wind up having Newton's method converge to this one. If we pick a starting point anywhere over on this side, we'll wind up with Newton's method converging to this point. So depending on where we start, we'll converge to one of the 2 different solutions that this particular equation has. Okay. So let's see, what else did I want to do? These are my 2 examples of cases where things fall apart, where things don't work. Let's do some examples where things do work. So let's take a look at examples that work. I'm going to go back to that same polynomial we wrote at the very beginning. It was a cubic. And I want to take a look at that one. So I want to think of my f of x equals x cubed, I think it was minus 3x minus 4. If we graph this, it's a cubic. I'm going to give you just kind of a quickish sketch. I know the general shape of this thing, but really this graph is mostly coming from me picking a graph off of Desmos. It turns out, here's the x, here's y. Turns out the 0 that we're going to be interested in is right about here. It goes through, let me get my scales of my axes here. It's going to go through this point. The graph winds up looking something like this. Here's the y equals f of x. And again, this is just something I picked up basically from Desmos. So just use some sort of graphing calculator to get a sense of what this picture looks like. But I want to just see what is our formula going to look like. So let's take a look at what Newton's method will look like for this example. The things we need for Newton's method is what f of x is and what f prime of x is. Remember, our formula is this. We want xn plus 1 to equal to xn minus f of xn divided by f prime of xn. So this is what tells me that I'm going to need both f itself and f prime. And so just to remind ourselves, f of x we just wrote down. It was x cubed minus 3x minus 4. And what is the derivative of that, f prime of x? Well, this term will become 3x squared, and this term will become a minus 3. So there's what the derivative looks like. And so for us, our specific version of Newton's method for this will look like the following. So we get xn plus 1 equals xn minus, the numerator is going to be x cubed minus 3x minus 4. And again, these are evaluated at xn. And I'm dividing by f prime of xn, so 3xn squared minus 3. Just basically plugging that guy there, that guy there. So there's our formula. If we try x1 equals 2 as our starting point, what we would get is we would actually plug this number in to get the following. x2 is going to be equal to, looking at our formula here, so in our case n is 1 and n plus 1 is 2. So I'm going to use x1 to predict x2. That's all I'm doing. Everywhere xn shows up in this formula, I'm going to plug in the number 2 because I'm basically treating all these xn's as x1, and then it'll spit out x2 for me. So in this case, our formula will be 2, there's xn, minus 2 cubed minus 3 times 2 minus 4 over 3 times 2 squared minus 3. And I'm just going to plug these numbers into a calculator. I mean, we could do it by hand if we wanted to. These are all going to be integers and we'll just get a fraction. But basically, you know, we'd have 8 minus 6 minus 4, so 8 minus 6 is 2, minus 4 is going to be negative 2 in the numerator. Down here we'll have 2 squared is going to be 4, times 3 is going to be 12, 12 minus 3 is 9. This winds up being 2 minus negative 2 ninths. If we do that in the calculator, that is 2.2222222, right? 2.2 repeating. We'll use that for our x2. So x3 is going to be this number, 2.222222, dot, 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 minus plugging it in all those same places. 2.222222222 dot 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 cubed minus 3 times 2.2222222 minus 4. There's our big, long, hideous numerator over 3 times 2.2222222 squared minus 3. And we would plug that in, and it would give us a number that was approximately 2.1962. And we would do that to find x4. Same idea. And basically you would go until the number that you get here, so coming back to our x3 value, until the number kind of stops changing. Then you'll know you've converged to the appropriate number, however many decimals you want. If you want 3 decimals, repeat this process until the first 3 decimals stop changing, and you'll know you're pretty much converged to the correct answer. But the point is, this isn't a method that's meant to be done by hand. Technically, back when Newton invented it, that's exactly what he did. He did it by hand. But it's really something that's easy to program in a calculator on a computer, and it's going to be something that we'll take a look at. I will post a video of how you can do this in Excel to make it go so much faster. I've already found a video of somebody else giving an explanation. I think it's better than the one that I could give. So I'm just going to post that video to show you how to do this on Excel. But long story short, so in general, don't do these by hand. Use a computer, or at least use a calculator. And I'll show you again. I'll post a video of how you can do these problems in Excel. But even for the homework, that's what I'm suggesting. You don't need to be doing these by hand. Do it in Excel. That will be a separate video. Let me give you one last example. I think this is the last example I want to show you. Let me just go through my notes here real quick, make sure I'm not missing anything. Yeah, this is the last example I want to show you. One of the main reasons that this was developed was to find roots, to calculate like square roots, cube roots, fourth roots of actual numbers before there were computers, before you could just plug it into the calculator and have it spit out the answer. So Newton's method can be used to find roots. And that's actually the reason that back in all of your algebra classes, you may have heard these points, these x-intercept points, let me see here, these x-intercept points referred to not only as zeros, or the x-intercept, but you may have heard them referred to as roots. Find the roots of this function. That's exactly what we're going to be doing here. So that's where that usage of the word roots comes into play. Okay, so let's say that I want to find the 6th root of the number 2. So I want to find the 6th root of the number 2, accurate to 8 decimals. So 8 decimal places. What we need to do is we need to find an equation that would have that particular number as its x-intercept. So we need to find a function f of x equals 0, or an equation rather, I should say. So an equation, let me erase that real quick. An equation, equation f of x equals 0 that has 6th root of 2 as a solution. And so the easiest way to do that is basically think about something like this. If I just did x to the 6th minus 2 equals 0. If I were to try to solve this, algebraically, pen and paper, the first thing I would do would be to move the 2 over the other side. We would get x to the 6th equals positive 2. How do you get the x by itself? How do you undo the 6th power? You take the 6th root. And so we take the 6th root and get that x equals the 6th root of 2. And so this is going to be sort of the pattern that you'll see this type of equation. Right? If I wanted the cube root of 7, I would do x cubed minus 7 equals 0, and that would give me x equals the cube root. Come on. Cube root of 7. So this is kind of the idea. You can follow this pattern in general to find an arbitrary root of an arbitrary number by setting up the equation the way that we have here. So that's what we'll be doing. Let me erase this one for now. We're not worrying about that one. Okay. So this is our f of x. So our f of x is equal to x to the 6th minus 2. And what is our f prime of x equal to then? Well, it's going to be 6x to the 5th. And so Newton's method gives us the following. So we get that my xn plus 1 is going to be equal to xn minus the original function, so xn to the 6th minus 2, divided by the derivative of the function, 6xn to the 5th power. Pick some number, preferably one that you think is close. So I'm going to pick x1 equals 1. This is kind of one of the tricky parts of all of this, is how do we pick our starting point? So far I've just told you what to use, but how do we decide what's a reasonable thing to pick? Well, looking at this one, I just kind of want to get something that's close. And so obviously if I were to plug in x equals 1, so x1 equals 1, if I plugged in 1 right here, I'd get 1 to the 6th, which would still be 1, minus 2, which is negative 1, which isn't so far from 0. I mean, it's not close, but it's not far. Whereas if I picked a number like, I don't know, 10 to the 6th minus 2, right? 10 to the 6th, we're talking about, what is that, like a million minus 2 equals 0. Not even close. So pick a number that's at least on the right order of magnitude. In this case, 1 seems like a reasonable guess. It's going to be a number bigger than 1, but you know, by the time we pick the number 2, for example, 2 to the 6th is, got to do this one in my head, is that 64, I think? So 2 times 2 times 2, 2 times 2, yeah, 64. 64 minus 2 would be 62, which is much further. So it's going to be a number between 1 and 2, but it's definitely going to be closer to 1. And so that's why I'm picking x1 equals 1. I'm just trying to get a number that gets close. Whoa. Close to satisfying this equation. So that's what I'm doing. So for us, if we go through this, we'll have x1 equals 1. We'll plug it in. I've just pre-computed these values, so you can try this on your own on a computer using the method that I'll show you in the next video using Excel. The number we get after this for x2 turns out to be about 1.16 repeating. x3 works out to be, I guess I should make these approximate symbols we're starting to round, 1.1264436, something like that. X4, repeating the process again, will give us 1.122497707-ish. X5, I get 1.1224122246205. By the time I get to X6, I get 1.122462205 again. And at this point, we've seen this is 1, 2, 3, 4, 5, 6, 7, 8 digits. It hasn't changed, so same to 8 digits. We have found our solution accurate to 8 decimal places, 8 digits. So we have our converged solution. Accurate to 8 decimal places. Okay, so that's the approach. Again, look for the other video. I'll put a link to it of how you can do this process in Excel really quickly. It's much better than doing it by hand. Please don't do these by hand.